All right, so number 50 will the problem here is going to ask you to determine the domain of each of the following functions, and you want to do this without graphing. So don't attempt to graph these. Think about what type of functions these are, and that's going to help you to determine the domain. So for example, letter A, here's my function. You have h of x is equal to x squared minus 7x plus 2. All right, now one of the things you need to recognize is that this is a quadratic function. In particular, let me put the word quadratic function, but in particular, one of the things you learned was that this is also a polynomial function. All right, so let me go ahead and put this is also a polynomial function. And one of the things you learned when talking about a polynomial function, one of the things you learned is that a polynomial function, when you look at the graph of a polynomial function, it is a continuous function. In other words, it'll look something like this. It's a continuous function. There are no gaps in the graph, there are no breaks, there are no asymptotes. It is just a continuous function. And so when you have a polynomial function, and remember a quadratic function is also a polynomial function, because if you look at the graph, let's say this is the graph, this parabola, it is a continuous function. So a polynomial function, if you look at the domain, if this is your y-axis and this is your x-axis, if you look at the domain, remember this means it keeps on going like this. So you're going from negative infinity in terms of the domain now. You're going from negative infinity all the way to positive infinity. And so that's the domain. So the domain of all polynomial functions, the domain of all polynomial functions will always be all real numbers. All right, so it's always going to be all real numbers. Now, in terms of interval notation, which is what you're going to use, you're going to write it as the domain. You're going to say, in terms of interval notation, you'll say negative infinity to positive infinity. And so that's your domain. Now, one of the polynomial function you need to be aware of that sometimes throws student is that of a linear function. So a linear function looks like this, right? And so you may say, well, that doesn't look like these curves you're drawing. You're right, it doesn't. It doesn't look like a curve that increases and then all of a sudden decreases, right? See how this decrease and all of a sudden increase? This here, for this one I've drawn, it's always increasing. But the point is the word continuous. Continuous. And so you want to look for that. So when I trace over that graph, it is a continuous function. So there are no breaks in the graph, there are no holes, and so on. So remember when we talked about piecewise functions? Piecewise functions, and so we looked at a graph, let's say that looked like this. Let me just kind of draw it like this. We saw this, and then there was another piece to it that did something like this. That would not be a polynomial function. This is not a polynomial function. And the reason it's not a polynomial function is because when I trace over it, notice I'm going from left to right, so when I trace over it, I have to jump to get to this other part. So there's a jump, so it's discontinuous. So this is discontinuous. So it's a discontinuous function. All right, and so this discontinuous function is not a polynomial function. Okay? So a polynomial function is a continuous function that looks like this. So you have this quadratic function, you have this linear function, all those are continuous functions. And when you talk about the domain, and these are all polynomial functions, and when you talk about the domain of these polynomial functions, the domain is going to be from negative infinity to positive infinity. It's always going to be all real numbers. Okay? So then we look at letter B. You have, let's see, you have f of x is equal to negative 3x to the fifth plus 2x squared minus 7x. So again, you want to do this without graphing. So think about what kind of function this is. So if you look at this function, this is also a polynomial function, isn't it? It's also a polynomial function. So the first two were polynomial functions. So if you were to graph it, which you don't want to, but if you were to graph it, it would be a continuous function. And the domain would be all real numbers. So the domain would be negative infinity to infinity. And just kind of show you, this is what the graph of this function looks like. So here's the graph of this function that right here. So that is, let me go ahead and write it. This is f of x equals negative 3x to the fifth plus 2x squared minus 7x. And so the graph is this. And so notice when you go from left to right along the x-axis, so this is the x-axis right here. When you go from left to right, I'm going from, and remember it keeps on going, right? So you're going from negative infinity all the way to, and then remember your x values, the domain's the x values. So I'm going from, so every point in this graph right here, every point in that graph is going to have an x value that's going to be from negative infinity all the way to positive infinity. All right, so the domain of all polynomial functions will be all real numbers. And in terms of interval notation, it's negative infinity to infinity. All right, so let's look at C. Now C, you have this function. You have h of x equals the square root of x plus 7. Now that's not a polynomial function. So we're looking at a square root function. All right, so one of the things you have to remember when dealing with square roots, now remember this is square root, so the index here is 2. Remember? So if there's no number there, it's understood to be 2. So that's square root. So it turns out though that whenever you're dealing with a square root function or a radical function whose index, remember that's called the index right here, whose index is even, remember you can only take the square root of a positive number or 0. Okay? So you got to ask yourself then, when I find the domain of this square root function, I have to make sure that this radicand, which is x plus 7, must be positive. Remember, greater than 0 is positive, or it can be equal to 0. The radicand must never be negative. All right, so if you take, for example, if you take the square root of a negative 6, let's say, I want to show you what that's going to look like. So if you take the square root of a negative 6, so square root, square root negative 6 and press equal, you get this domain error. So you cannot take the square root of a negative number and get a real number. So when finding the domain of a square root function, you're going to take the radicand, which is x plus 7, and you're going to set, in this case it's x plus 7, and you're going to set it greater than or equal to 0. All right, and you just solve for x. So when I solve for x, I get x is greater than or equal to negative 7. So what I found is that any real number greater than or equal to negative 7 is going to be in the domain. So in terms of interval notation, remember that looks like, so here's negative 7, greater than or equal to, so since there's an equal sign, it's a closed circle, and you're going to the right. So then your interval notation, you can say from negative 7 all the way to infinity. So the domain will be negative 7, no bracket. I'm sorry, there is a bracket, excuse me, bracket. All right, bracket, negative 7, that's a bracket. Bracket, negative 7 all the way to infinity. All right, because negative 7, remember this can be 0. So when I substitute negative 7 plus 7 is 0, and I can take the square root of 0. Square root of 0 is 0. All right, so bracket negative 7 to infinity. All right, so remember when the index is even, you have to find the domain, you have to set this greater than or equal to 0. All right, and then D, So in D, we have k of x. Oh, and the graph looks like this, by the way. So here's the graph. So there's the graph of this function I just drew. It's h of x equal the square root of x plus 7. All right. And see, this is what the graph looks like. So there's one arrow. It looks like this. And this little point here, the point where it starts, that x coordinate right here is negative 7. That's what that is. So the coordinates of this point, the coordinates is negative 7, 0. That's the coordinates of that point, negative 7, 0. So the domain then, remember when looking at the graph and you find the domain, you always go from left to right. So the domain, the graph starts when x is equal to negative 7 all the way to infinity. All right? Okay, and then D, you have k of x is equal to 3x minus 1 divided by 2x plus 5. And so remember, when you have a rational, and this is a rational function, so let me go ahead and write it out. This is a rational function. And so when you have a rational function, remember your denominator can never be 0. So to find the domain, of this rational function, you're going to set the denominator equal to 0. So you're going to say 2x plus 5 equals 0. And use to solve for x. So when I solve for x, I get 2x equals negative 5, and so x is negative 5 halves. All right, so what that means is that my domain will be every real number except this. Domain is all real numbers except x equal negative 5 halves, or x equal negative 2.5. All right, so that's the domain. All real numbers except x equal negative 5 halves, because negative 5 halves makes the denominator 0, and you can never divide by 0. So remember, if you have, let's say, 6 divided by 0, you should get divide by 0 error. All right, so you cannot divide by 0. All right, so what you can then do to help you to find the domain in interval notation is you're going to put this number on the number line, negative 5 halves. You're going to cross it out because you can't use it. So what that means is that all these other numbers here, don't forget the arrow, all these other numbers here will be your domain. So the domain, when going from left to right, remember, always go from left to right, you're going from negative infinity to negative 5 halves, union, and then negative 5 halves to positive infinity. Now, when you do this in interval notation, you're going to say parentheses, negative infinity, negative 5 halves, parentheses. See here, this one was a bracket because I can take the square root of 0. But here, I cannot divide by 0. So negative 5 halves makes that denominator 0. So I cannot divide by 0. So that means that negative 5 halves is not in the domain. So that's why you need parentheses. And then union, and then the second interval. See, there are two intervals here. This interval and this interval. So, and this interval is negative 5 halves to positive infinity. So parentheses, negative 5 halves, positive infinity. Okay? That's the domain. Now, when you look at the graph, and you're going to learn how to graph this in a week or so, but when you graph this, this is what it looks like. That's the graph right here. So you see it's not a polynomial function. And in fact, you see this number right here, this negative 5 halves? You're going to learn that this negative 5 halves in relation to this graph here. So here's x equal negative 2.5. So it's about right here. I'm going to draw this line. So x equals negative 2.5 right here. All right, so that line I'm drawing, you don't know this yet, but that line I'm drawing, and I'm not doing a very good job with it, but that line I'm drawing, it's a vertical line. That line I'm drawing is called the vertical asymptote, asymptote, vertical asymptote. All right, that's what that is. That's called the vertical asymptote. So what happens is that the graph gets, as you see how the graph here, as you go from left to right, the graph gets closer and closer and closer to this vertical asymptote. See the dotted line? That's a vertical asymptote. And on this side does the same thing. So when you go over here, like you're going this side towards the vertical asymptote. See how it's getting closer and closer and closer to it without touching it. It never touches it or crosses it. So, so that's called the vertical asymptote, and that's what we found here. So in terms of this domain, this number we found for this particular rational function is called the vertical asymptote. That's the vertical asymptote. So when you graph it, and you're going to graph some of these soon, then you're going to notice that this number is actually a vertical asymptote. All right, very easy to graph, not that difficult. Now, just to let you know though, because it is possible that this, now remember, this is actually a vertical asymptote, but there are rational functions, in which you don't have a vertical asymptote. What you have, sometimes what you have is a hole in the graph. A hole, or just write the word hole, H-O-L-E. Sometimes you'll have a hole in the graph, and that's not the case here, but sometimes you will. And that occurs, by the way, that occurs when, and one of the things you're going to learn is that when finding the domain, you're going to factor the numerator and the denominator. We didn't do that here because it's not factorable, but you're going to factor the numerator and denominator, and if there are any common factors, then that's where the hole will be. That's what that is. The hole will be where the numerator and the denominator have a common factor. Okay? All right. So you're going to learn about all these pretty soon. But for letter D, all you have to do to find the domain is just to set the denominator equal to 0, and then you put that in the number line, cross it out because it's not part of the domain, and notice you have two intervals here, and so that's why you see two intervals here. Okay? All right, so that was number 50. Okay, so when we look at number 51, all right, for 51, they're asking you to determine the end behavior. All right, determine the end behavior of, and these are going to be polynomial functions, of each polynomial function. All right, so for example, let's look at A. So A, we have f of x is equal to 3x to the fifth minus 7x plus 4. All right, so when determining the end behavior of a polynomial function, you need to first of all determine your leading term. Your leading term, you have to find that first. And the leading term doesn't mean the first term you see. The leading term is a term with the largest exponent, with the largest degree. So the largest exponent, largest degree. Okay? And so in this case, x to the fifth is my largest, well, 5 is my largest exponent, so the term, the leading term here is 3x to the fifth. All right. Now, once you find the leading term, you need two things to determine the end behavior. You need to know whether the exponent is even or odd. So notice the exponent is odd. Okay? And the leading coefficient, whether it's positive or negative. And so notice my leading coefficient is positive. So leading coefficient is positive. And those are the two things that you need in order to determine the end behavior of a polynomial function. Once you know the whether the exponent is even or odd, or whether and you need two things, and the leading term is positive or negative, then you'll be able to tell me the end behavior of that polynomial function. And remember what I mean by end behavior. So what I mean by end behavior is this. So remember, polynomial functions look like this. So you think about the left side and the right side. So the left side behavior and the right side behavior. So let's say we have this polynomial function that looks like this. Okay? So this is the left side of my end behavior, and this is the right side. That's what I mean. I don't care what happens in between those. So you have these turning points here. I don't care about that. All I want to know is this end behavior. So what is the graph doing on the left side? What is the graph doing on the right side? And so if you had this idea here, you would say the end behavior, you would say the function rises on the left, because that's what it's doing, it's rising, and it's falling on the right, and falls on the right. And that's all you're saying. Okay? All right, now to help you with these though, we talked about this fact. There are two functions, well, four functions you want to remember, and that is this. And that's going to help you to determine the end behavior of all polynomial functions. So we talked about this in class, so you have to know these, and that's going to help you. So for example, f of x equals x squared. Okay? So notice the degree is even, my my coefficient's positive. All right? So the exponent is even, coefficient is positive. And so when I think about the graph, remember the graph looks like this, right? Looks like this. So the end behavior, you would say, rises on both sides. That's what that is. So whenever you have a polynomial function in which the leading term, the exponent, is even and the coefficient is positive, the end behavior rises on both sides. So you'd say rises on both sides. Okay? The other thing you want to remember is this one. F of x equals negative x squared. And so remember that negative is a reflection about the x-axis. So it will look something like this. Reflection about the x-axis. So notice the degree is even. So the exponent is even. This time, though, the leading coefficient is negative. In this case, it's a negative 1. So coefficient is negative. So whenever the degree is even, so remember the degree is even means that the arrows are pointing in the same direction. That's what that means. So notice the degree is even, the arrows point in the same directions, either pointing up or pointing down. Okay? If the coefficient is positive, they rise on both sides. If the coefficient is negative, they fall on both sides. Okay? So in this case, you'd say fall on both sides. All right, so when the degree is even, it's easy. When the degree is even, they rise in the same they go in the same direction. The end behavior is in the same direction. If the coefficient is positive, they both go up. If the coefficient is negative, they both go down. The third one you want to remember, I'm going to call this g of x, is x cubed. And so remember, x cubed looks like this. So that's the graph of x cubed right here. Okay? So notice that the end behaviors are in opposite directions. So whenever the degree is odd, whenever the exponent is odd, you have opposite directions here. Okay? Whenever the degree is even, same direction. Whenever the degree is odd, opposite directions. So on this side it rises to the right, falls to the left. Okay? Notice though the coefficient is a positive 1. So coefficient is positive. And so when the coefficient is positive, the left side is going to fall, the right side is going to rise. So left side falls, right side rises. And then if you look at, let's say, negative x cubed, remember that's a reflection about the x-axis, that negative here. And so instead of doing this, it's actually going to do this. And instead of doing this on this side, it's going to do this on that side. So notice this is negative x cubed. As long as you know what x cubed looks like and you know what negative x cubed looks like, you will then be able to answer all these questions, determining the end behavior. So notice that, remember we talked about this, when the degree is odd, they're in opposite directions. One side rises, the other side falls. The coefficient here is negative. Whenever the coefficient is negative, it rises on the left, falls on the right. Okay, so as long as you know what this graph looks like, you'll always be able to answer those questions. So the exponent is odd and the coefficient is negative. Whenever that's the case, it's going to rise on the left, So that's the left side, that's the right side, and falls on the right. Okay? All right, so now let's look at this one. So notice the leading coefficient is 3x to the fifth. The exponent is odd, so the exponent's side, remember, is opposite directions. The coefficient's positive. So the coefficient's positive, you have to remember this one, the x cubed one. So left, right. So you're going to say f of x rises on the right, falls on the left. That's what's going to happen. Okay? Rises on the right, falls on the on the um, on the left. And this is what it actually looks like. That's what it looks like. See, so it falls on the. So this is f of x equal 3x to the fifth minus 7x plus 5. So that's what it looks like. So notice it falls on the left, rises on the right. Okay, you're not interested in all these turning points here. You're just interested in the end behavior. And all you need for the end behavior is the leading coefficient, the exponent, whether it's even or odd, and the coefficient, which is whether it's positive or negative. All right? Okay, so let's look at B now. So in B, you have this. You have g of x is equal to negative 4x to the seventh plus 3x to the fourth minus 7x plus 1. So the leading coefficient is going to be negative 4x to the seventh because of the exponent being the largest. All right, so the exponent is odd, and the leading coefficient is negative. So in that case, you want to think about negative x cubed. So remember, negative x cubed looks like this. So rises on the left, falls on the right, and that's what this one will do. So now, just to be a little careful, I'm not saying that this graph is this graph here. Okay, it's not. I'm just saying the end behaviors. I don't care what happens between them. I just want to know the end behaviors. So you're going to say g of x rises on the left and falls on the right. Okay? All right, let's look at C. So in C, we have h of x is equal to 3x to the fourth minus 3x plus 4x cubed. All right, so you got to look for the leading coefficient. So I'm sorry, the leading term. The leading term is 3x to the fourth, and the exponent is even, and the leading coefficient is positive. So in that case, you want to think about x squared. So x squared looks like this. And so notice that whenever the exponent's even, the end behaviors point in the same direction, either up or down, right? And if the coefficient is positive, they're both going to point up. So you're going to say h of x rises on both sides. All right, so that was C. All right, let's look at D. So D, we have this. So here's D. We have k of x is equal to 4x squared minus 4x minus 3x to the 6. All right, so remember you got to look for the leading term. So the leading term doesn't always mean the first term you see. Notice this is my largest exponent, so my leading term is negative 3x to the 6. So be careful, since it's negative, you have to keep the sign. So the leading term is negative 3x to the 6. So the exponent is even, coefficient is negative. And so in that case, you want to think about negative x squared. So when you think about negative x squared, if you remember what that looks like, and hopefully you do, the end behaviors are pointing the same direction and you're pointing down. All right, so the same thing's going to happen here. So k of x will fall on both sides. Okay? And then we have one left, and that's e. So e, we have k of x is equal to 7 minus x squared. All right, so notice my leading term is this one here. So the leading term is negative x squared. So the exponent is even. The leading coefficient is negative. And so that's going to be the same as this one. And so you'll just say k of x will fall on both sides. And that's it. So that was numbers 50 and 51. All right. And so hopefully these problems will help you to understand those concepts a little bit better. All right, so that is the end of the key to those two problems.